everyone in the AI field is racing to scale models and deploy them faster. But to achieve superintelligence, we need to build infrastructure that makes hardware diversity low friction. Good afternoon, everyone. My name is Ajit Mathews, and for the past 5 years, I have been leading Meta's AI acceleration organization, the team behind our accelerator programs, and the PyTorch first software stack that ties them all together. Today, I will talk about how we are building the software rails that turn hardware diversity into a superpower in Meta's race to superintelligence. So, most of you know this, but our products, Facebook, Instagram, WhatsApp, Messenger, serve 3.5 billion people each month. Every story ranked, every ads delivered, every LLM assistant response runs on top of the AI infrastructure at a planetary scale. So scaling to billions has meant scaling every layer of the stack: data, storage, networking, and especially compute. That scale has driven constant reinvention of our AI infrastructure and the hardware that powers it. And with that scale come diversity of models, of workloads, and of hardware. And that's where the AI infrastructure story really begins, with the challenges that comes from operating at this scale. So I want to talk about few challenges and two specific challenges. Our first challenge is AI workload diversity. Across Meta, we deal with a wide range of workloads, from ranking and recommendation to large language models, and multimodal systems. Each one stresses compute, memory, and network bandwidth in very, very different ways. New architectures, algorithms, and numerical techniques emerge constantly. A workload that is compute bound today might be a memory bound or a communication bound in the next generation. The evolution is faster than any hardware refresh cycle. The takeaway is simple: one size does not fit all. To keep up, we need flexible silicon to software co-design and infrastructure that can adapt as quickly as the workloads and models themselves. So the second challenge is AI hardware diversity. As workloads diversify and scaling demands grow, hardware keeps expanding. And that explosion of platforms brings its own challenges. For example, the hardware landscape at Meta has exploded from NVIDIA to AMD to our own MTIA, which is Meta's training and inference accelerators. It is difficult for modeling and AI engineers to think about building and optimizing workloads for different types of hardware. If new hardware necessitates writing tons of libraries, kernels, and applications, then there will be a strong resistance to adopt new hardware. I want to give you a bit about MTIA, which I talked about is our Meta Training and Inference Accelerator. We built MTIA specifically to address the unique workloads that power our products. We started with a focus on ranking and recommendation, a workload that is very specific to Meta and a core part of our business. Our first chip was relatively small, optimized for ranking and recommendation inference. This chip is now deployed at scale in our data centers, primarily serving our ads workloads, and has given us massive efficiency and benefits over vendor silicon. From there, we extended the program into training and next generation Gen AI chips, creating a roadmap of accelerators optimized for different AI domains that we have internally at Meta. We know that building custom accelerators is a significant integration lift. The MTI, it's about hardware and software co-design. Co-designing hardware with a PyTorch first software stack is the only way to hit our product SLOs for latency, power, and cost at meta scale. Just as important, owning one backend deeply hardens the architecture and makes all other backends stronger. Each generation becomes faster to deploy, easier to program, and better integrated into Meta's AI stack, spanning ads, Facebook, Instagram, and GenAI. That's the context of MTIA family of accelerators. So, heterogeneous hardware gives us scale. Software is what makes it low friction. And success now depends on how we make all this diversity work together in software by meeting developers where they are. Most of Meta's modeling and infrastructure engineers live in PyTorch, and that's exactly where we want them to stay. They expect a seamless, fully integrated experience, one where hardware feels fungible and invisible to them, so they can focus on building models, not porting them. Our job in AI infrastructure to make that really possible for them. We also want to use this opportunity to advance the state of the art, pushing the frontier of heterogeneous hardware support through Triton, Inductor, and AI kernel generation for the AI hardware architectures we support across Meta. So, if meeting developers where they are is really the goal, what does that really mean in practice? We aim for performance portability, where code written once works perfectly across hardware. At Meta, we think about this through three pillars that guide how we build towards that vision. First is fungibility. Common operators, PyTorch operators, need to just work with reasonable performance across hardware. Second is the velocity. Machine learning engineers and researchers should be able to prototype and try new models and algorithms without friction. And third is the performance. For the most critical innovations, there must be a way to invest and achieve roofline performance on each of these different devices and systems. These three pillars, fungibility, velocity, and performance, define what success looks like for our developer experience and shape how we design the entire PyTorch stack. Delivering for those developer expectations means that hardware heterogeneity has to exist not just at the PyTorch level, it has to permeate the entire software stack. At Meta and across the industry, we are investing across these layers to enable hardware heterogeneity and close that gap. So a few examples, and we heard that in the panel too. At the foundations, projects like Popcorn explore AI-assisted kernel generations. Collective communications to enable large-scale training, distributed inference, and device-initiated comms, which you will hear more in this PyTorch conference. And at the application level, frameworks like VLLM, delivering high-performance inference on diverse hardware is important. Gaps at any of these layers, what we see, from foundational components to domain-specific frameworks, break the ability for developers to use heterogeneous hardware without friction. So we have now seen how hardware heterogeneity has to span the full stack. But for most developers, the stack starts right here within PyTorch. It's the bridge between the frameworks and the hardware, and it's really where the story begins. Hardware vendors can optimize implementation without user even needing to know what language is being used to access the hardware. There has been extensive investment by companies in optimized libraries such as Cutlass, Qt, CUDA libraries, RockBlast, Composable kernel, all of which PyTorch hides from the user. PyTorch seamlessly hides that complexity from the user, giving us a unified interface and functional fungibility across these common operators. But as the platform expands, less expensive solutions are needed to provide the fungibility on new hardware, like, for example, MTIA. So, as the number of hardware platform grows, we need more scalable ways to bring up new backends quickly. And that's exactly what Torch-Inductor was designed for. Torch-Inductor enables abstractions and automation that can reduce the cost of new hardware. It's compiler built into the PyTorch that generates Triton code for us. And it already supports many PyTorch ops for GPUs, which can be repurposed to provide rapid operational op coverage on new backend, for example, like MTIA. An added benefit of Inductor is that it also enables compiler fusions when a developer switches to the torch.compile flow. By enabling broad operator coverage, directly through Inductor, we enable composition of more complex graph optimizations without much additional investment. We are pushing boundaries here too, enabling eager mode Inductor to enable production deployments of models on non-GPU hardware like MTI. And the foundation that makes Inductor so powerful is Triton, the Python-based kernel language that lets us express and optimize kernels across various architectures. So, in short, Inductor turns functional portability into a performance portability that I talked about, adapting PyTorch workloads automatically for any supported hardware backend. So, Triton was developed for GPU kernel authoring in a Pythonic language, which meets GPU developers where they are. However, for MTIA, we have invested in Triton for MTIA, and it's been a great success. It unlocks the potential of MTIA hardware through abstractions that enable development in a very familiar Pythonic language without having to worry about the hardware details. It enables a rapid experimentation with reasonable performance. And we have seen significant performance gains through additional manual kernel fusions for eager mode execution. We have put heavy emphasis on vanilla Triton language support to make sure that the users with the GPU Triton experience can onboard to the MTIA easily. Many Triton GPU kernels have been ported to MTIA with no or minimal modifications, including various attention variants from internal kernel libraries. We make sure that the common patterns in Triton work well out of the box on MTI through compiler transforms. To make all of this work efficiently, we built a new MLIR-based Triton backend for MTI from the ground up, which applies compiler transforms that automatically adapt Triton kernels into MTI architecture. Keep an eye out for our upcoming paper on Triton for MTI, where we'll share more details soon. Now let's see how Inductor and Triton work together to rapidly expand operator coverage on MTIA. Supporting every torch operator on new hardware can be expensive, but by combining Inductor and Triton, that has dramatically lowered the cost for MTIA. First, Triton enables many implementation details to be left to the compiler, whether the GPU or MTIA, really reducing the cost of initial operator coverage. Second, on top of Triton, Torch-Inductor provides an even higher level of compiler to generate Triton code for PyTorch operators, reducing the investment needed for broad operator coverage. So with Inductor plus Triton, we quickly achieve great operator coverage on new hardware. Once that foundation is in place, teams can surgically tune and improve the performance of few bottleneck kernels that matter most, and they can do it guided by the real production data. Once we have achieved broad operator coverage through Inductor and Triton, the next question becomes, how do we keep up with the new operators as model continues to evolve? As new architecture emerge, operators are often created experimentally, quickly iterated, optimized, and then deployed at scale. For this, we leverage Triton to rapidly build and test new kernels directly on MTIA. Triton lowers the risk for developers doing this early prototyping on MTIA because the same code can also run on other hardware backends, as I talked about. That makes innovation fast, low risk, and portable, exactly what we need as models and hardware are both evolving. Of course, there are still few cases that we need to go deeper, where hitting absolute peak performance requires full control of the hardware. So let's look at how we handle that. Even with everything that we have built, there's always a small number of performance critical kernels where we will need to go closer to the metal to reach the device's roofline. Think of cases like flash attention. They require custom fused implementations and deep hardware level optimizations to get the last few percent of performance. For these cases, we expose two paths. First, we have extended the Triton language for MTIA to give developers low-level control, similar to the Qtile style tuning, but without code porting between platforms. Second, we offer a C++ explicit programming model for teams that need to control every detail: vectorization, memory layout, scheduling, you name it, to squeeze out every bit of performance. Both paths are supported by rich performance analysis and debugging tools, so teams can optimize with confidence. These solutions are obviously not portable across architectures that have steeper learning curves, but they must exist, even if rarely used, to guarantee that automation will never block reaching the performance goals for production release targets for a model. They are necessary condition for production hardware at meta scale that we are talking about. So everything we discussed, Inductor, Triton, and even the low-level paths, is already running in production on MTIA. Other architecture may see the majority of workload running using low-level coded libraries, but at Meta, we can't afford to take this approach across many generations of hardware that we simultaneously support. So we're pushing on Triton and in many cases Inductor to provide low friction, high performance solutions that generalize across these hardwares. So to make this more real, the graph shows a bit of info on our Triton trajectory in workloads running in full production on one generation of MTI device. The results are averaged over a wide range of models from different Meta work products. There are two key takeaways. First, the quarter over quarter growth is significant. Triton enables us to move fast and avoid reinventing those kernels from scratch. The second, a large fraction of our production workloads are now live at massive scale using Triton. Not 100% of kernels are using Triton, but that is often simply because the team chose to use a different solution of one of the many reasons that I discussed earlier. But the direction is clear. Triton and Inductor are already powering Meta's heterogeneous production stack. So everything to this point is essential for building foundational infrastructure. The next frontier is AI-assisted kernel generation. And we are always looking at 10x increase in the pace as we adopt heterogeneity at scale. At Meta, we already have active efforts in this space. I talked about including the public popcorn project for AI authored kernels. The idea is simple: use large language models to propose kernel candidates, then automatically compile, execute, and validate them against reference implementations. We think of this evolution in two phases. The phase one, AI generates candidate kernels for humans to review, augmenting and experimenting and accelerating the expert kernel authoring. Phase two, as a verification and validation improve, AI moved towards fully automated kernel generation, removing humans from the loop while improving both velocity and correctness. If we get this right, we end up with a world where hardware heterogeneity feels seamless and self optimizing. How close we are to that world isn't clear yet, but the trajectory is clearly exciting. So we are already seeing promising results from AI generated kernels on MTI. So I want to share some info here. One of our internal kernel authoring systems, powered by large language models, has been able to generate and validate more than 120 PyTorch A10 ops in under 10 hours. Each kernel goes through automated compilation, execution, and correctness, and checks against reference implementation. These are still early experiments, but they demonstrate early potential at scale. The long-term goal is to achieve full operator coverage before even hardware powers on. Using only architectural specifications, essentially we want to make sure there's a day zero support for our new silicon. There are still open questions like, what's the best representation for AI to emit? Triton, compile IR, or even machine code? And how do we ensure performance and correctness as humans move further out from the loop? But even at this stage, AI is already accelerating kernel development and reducing friction in bringing up new hardware for production. We are seeing clear momentum towards a world where AI helps human write kernels, cutting weeks of work down to hours and freeing engineers to focus on really the hard problems. There's a whole set of topics we have had time to explore today, areas we are actively working on across Meta's AI infrastructure. Things like application frameworks about PyTorch, new work on data center scale fault tolerance that we discussed earlier, and how we are using AI itself to accelerate debugging and performance optimizations. Each of these areas evolving quickly, and they all connect back to the same idea: building the low-friction AI infrastructure that will carry us forward in the race to superintelligence. Because each of these areas deserves its own session, we will have a lot more to share the next time when we meet. Okay, so if this is the last slide, few closing thoughts. If there's one idea I want you to walk away from this talk, is that heterogeneous hardware is the path forward. It's always a huge challenge for Meta and for the entire AI industry. And at Meta, we have learned that scaling AI means scaling across diversity of models, of workloads, and of hardware. PyTorch gives us that foundation of fungibility. Inductor and Triton turns that foundation into real performance and portability. Low-level control ensures that automation never blocks the performance goals that we need to meet. And AI-assisted kernel generation pushes that progress into an entirely new level of speed. Together, they form a software rails that make hardware diversity an advantage, not a task. The race to superintelligence will be powered by bigger models and faster chips, but it'll be won through low-friction AI infrastructure that scales seamlessly across heterogeneous hardware and empowers ML researchers to innovate. Thank you and happy scaling. Enjoy the PyTorch conference.